Welcome everyone to our integrated project presentation. Our group comprises of 5 members, namely Timotheus Johnson, myself, Ng Ying Hui, and Iman Dafra Solehan, Siti Khalila Khalid, and our last member, Muhammad Azam bin Azahari. So for today, our presentation is comprised of 4 parts, which are the introduction, the reaction engineering 1 part, process modeling simulation, and last but not least, the separation process 2 part. So I'll give you a brief introduction of our case study. So for our case study, our main goal is to produce 3,000 tons of biodiesel a year from palm oil. So the main reaction here is transesterification, which is a reaction whereby triglyceride reacts with methanol aided with a catalyst, and we will get a mixture of fatty esters and glycerol. The fatty esters are also known as biodiesel, and the byproduct glycerol can be used in other industries as well. So for our main reaction, we will be using triolene with methanol aided with our catalyst, which is sodium hydroxide, and we will get a methyl ester and glycerol. The side reaction that could happen is saponification, which is the free fatty acid, palmitic acid, reacts with the catalyst, sodium hydroxide, and we will get soap and water. But for this case study, our main focus is on the main reaction. So this is the process flow diagram that we have designed, and basically this is comprised of 2 CSTRs and separation vessels, an absorber, and also an evaporator. So now I'll be introducing the reaction engineering 1 part. So for the type of reactor used, we have chosen CSTR, which is a continuous stirred tank reactor. The reason we chose this is because all of our reactants are in the liquid phase, and the CSTR is our best choice. And as for the catalyst and operating condition used, we are going to use an alkali catalyst, which is sodium hydroxide, and with the operating conditions of 55 degrees and 1 atmospheric pressure. The molar ratio of triolene to methanol is 1:6, and the concentration of catalyst is 0.28%. There are a few strategies that we have used to maximize the selectivity and yield of our biodiesel. Namely, we have 4 factors, which are the catalyst, the temperature, reaction time, and the stirring speed. For the catalyst, we are using an alkali catalyst, and the rate of esterification increases with the amount of catalyst. It's important to note that the amount of catalyst should not exceed 0.5 mole kilogram per oil to prevent saponification. For the operating temperature, with a higher temperature increases the rate of the reaction, but it's important to note that the reaction temperature should be lower than the boiling point of our alcohol of choice, which is methanol. Hence, our operating temperature is 55 degrees. For the reaction time, sufficient time is of course is very important, and the optimum time is 2 to 3 hours. As for the stirring speed, stirring is very important as to mix the immiscible layers within the CSTR. So the higher the stirring speed, the shorter the completion time until it becomes constant. So for the sizing of the reactor, here we can see a stoichiometric table that we have prepared, which is crucial to determine the size of the reactor needed for our desired conversion. And so for the first CSTR, our desired conversion is 60%, and we have calculated that the volume needed is 0.0165 meter cube. And it's important to note that the concentration of component A at the outlet of CSTR1 will become the inlet concentration of CSTR2. So our concentration of component A at CSTR1 is 0.0916 kilomole per meter cube. So lastly, in our second CSTR, our goal is to achieve a 90% conversion rate, and the volume that we need is 0.9226 meter cube. So I'll pass the floor to Timo to further explain on the process modeling and simulation.
Alright, thank you, Ying. So basically in this part, we are required to simulate the process from reaction engineering by using symmetry. So firstly, we have used NRTL as our property package as our reactants are in liquid phase. So firstly, we have connected 2 streams, which were methanol and triolene, to a mixer, and in the triolene stream, we have inserted the temperature value as 25, pressure as 1 atm, and mole flow as 0.64. And this value has been obtained from the reaction engineering. And for the mole fraction, we have kept triolene as 1. And for the methanol stream, we have kept both the temperature and pressure as the same as triolene, which was 25 degrees and 1 atm. And the mole flow for methanol was 3.85. And this value was also obtained from the manual calculation. The mole fraction for methanol was also set to 1. And once these 2 streams are once you have inputted the values into both these streams, we will then connect it to a mixer, and both these streams will be mixed. And once it has been mixed, we will connect it to a heater where we will increase the temperature from 25 degrees to 55 degrees. And also noting, since in our report we have also assumed that no pressure drop in our heater, we kept our delta P at 0 kPa. Next slide. So once we have heated the stream from 25 degrees to 55 degrees, the stream will then enter the first CSTR. And in the first CSTR, we have kept delta P as 0, and we have also set the volume for the first CSTR as 0.062 meter cube. And this value was obtained from the manual calculation. And we have also assumed that the activation energy as well as the frequency factor to be 45,000 and 42487.2 respectively. Once the stream is out from CSTR1, it will enter the second CSTR, and in that second CSTR, we have also kept delta P as 0, and the volume for that CSTR, we have kept it at 0.923 meter cube. And this volume value was also taken from the manual calculation. And in our slide, we've also shown the diagram of our process simulation. Next slide. So in this part, we'll be comparing our assumed conversion with the calculated conversion from the simulation. So for CSTR1, we have assumed that our conversion to be 0.6. However, our conversion that was obtained from simulation was 0.45. Hence, our error turned out to be 33.33%. And as you can see that our percentage error was large, and this was probably due to human error. In CSTR2, our estimated conversion was 0.9, and our calculated conversion came up to be 0.92. Hence, our error was 2.17%. And as you can see, our assumption of conversion for CSTR2 is more accurate compared to CSTR1. Now I'll pass the floor to Iman.
Thank you, Tima. I'm going to talk about the effect of feed temperature, feed composition, and feed flow rate on the reactor's performance. So the first effect of feed temperature, as we can see in the graph, if we increase the feed temperature, we also increase the conversion. This is because due to the high temperature, it creates high kinetic energy in the molecules, therefore increasing the chance of effective collision. So we can say that the feed temperature is directly proportional to the conversion. And also, due to the exothermic reaction, the temperature also increase along the reactor. Next. And for the second effect of feed composition on the reactor performance, if we increase the feed composition, we also increase the flow rate. However, if we increase the feed composition, it decreases the conversion. This is because if flow rate increase, the conversion decreases, and there is not much to explain. So we can say that feed composition is inversely proportional to the conversion. Next slide. So for the third effect of feed flow rate on the reactor performance, this is relatable to the second effect just now. So we know that when we increase the flow rate, it will decrease the conversion. So as we can see for the first graph, when we increase the flow rate of trioline, it will decrease the conversion slightly. However, for the flow rate of methanol, if we increase it, the conversion decreases gradually. So this is because we are manipulating the flow rate. So therefore, there is changes in the reactants molecule, so it also lowers the chance of effective collision. And also due to the residence time, because the flow rate is high, the process of mixing is fast, therefore decreasing the residence and also decreasing the conversion. So for this, we can say that feed flow rate is inversely proportional to the conversion. Now I would like to pass to Kalila to talk about the separation process.
All right, thank you, Gaffa. So I'll be continuing with the separation process part. And as you can see in this slide, this is the overall block diagram for our separation system. And the separation units for the system for biodiesel improvement are separation vessel, evaporator, and absorber. Next slide, please. And on the left side here is the schematic diagram for our separation process system. And dry washing technique is being used in this system because it is a waterless technique that improves fuel quality and overall reduces the production cost and time because there are no water is being used in this process. Next slide, please. All right, for the separation vessel is being used to separate the reaction products, which are the combination of biodiesel and glycerol. And separating glycerin before the methanol recovery process reduces the probability of the reaction reversing during the methanol recovery process. Next slide. And then a fatty acid alcohol ester is created by reacting a triglyceride with alcohol to form biodiesel. And methanol is selected in this study since it is the simplest and most reactive and least costly for all alcohols, and making it the product of choice for biodiesel manufacturers. Next slide. And then absorption in packed bag column with silica gel is being used in this, as absorbent is being used in this case study to purify biodiesel as an alternative to the commonly used water washing technique, which is resulting in fewer wastewater discharge concerns. And next, I'll pass to Azam.
Thank you, Kalila. I will now present on the calculations related with the separation process system. So the first unit is the separation vessel. As can be seen from the figure, the products from CSTR2 enter the separation vessel at 55 degrees Celsius and at atmospheric pressure. The separation occurs by settling due to the difference in density between methyl ester and glycerol. And it is assumed that 99% of methyl ester is separated into the top stream, while 99% of glycerol and unreacted triglyceride flows into the bottom stream. 60% of methanol is distributed into the methyl ester phase and 40% of it into the glycerol phase. Next slide. The crude biodiesel is then sent to an evaporator unit to remove excess methanol. The outlet liquid stream is assumed to have a methanol concentration of 0.1% kg methanol per kg of biodiesel. In order to achieve this, a total of 17.86 kilowatts of heat energy is required, which is provided by saturated steam at 140 degrees Celsius with a flow rate of 29.98 kilograms per hour. The heat transfer area required for the evaporator is 0.139 meters squared if the universal heat transfer coefficient is assumed to be equals to 1704 watts per meter squared Kelvin. Next slide. After the evaporator, the crude biodiesel is then passed through an adsorption column filled with silica gel as the adsorbent. The adsorption column is assumed to have a height of 60 inches and a diameter of 10 inches. 41.7 kilograms of silica gel is used with a saturated loading capacity of 0.1152 kg of glycerol per kg of silica. The breakpoint time of the column is 8.18 hours, which means that the adsorbent needs to be replaced about once every 8 hours of operational time. The resulting refined biodiesel contains 0.1% kg of methanol per kg of biodiesel and 0.044% kg of triglyceride per kg of biodiesel, which meets the requirement set by the EN 14214 specification, thus making it a high quality biodiesel fit for commercial use. Next slide. So that is all from us. Thank you very much for listening to our presentation.